All right, so now I'm going to introduce this idea of the matrix exponential. And the reason for this is because you're going to be able to express the general solution of a system of linear differential equations in terms of the matrix exponential. Okay, so so let's consider the case where A is a square matrix. All right, so motivated by the series expansion for the exponential function, right, which basically just says that e to the z is 1 plus z plus 1 over 2 factorial z squared, and so on. Right, so this is just the sum for k equals to 0 to infinity of 1 over k factorial z to the k. Right, we introduce the matrix exponential. Of this matrix A. So we're going to define this to be e to the A is the identity matrix, right, plus A plus 1/2 A squared, and so on. And again, this is the sum from k equals to 0 to infinity of 1 over k factorial a to the kth power, where it's understood that a to the 0th power is the identity, right? Which makes sense. Okay. All right. So obviously, it's like what we've done is to substitute. It's like this square matrix A. It's like for z, it's like this complex value z. It's like in the original definition of the exponential function, expressed in terms of the series expansion. So, all right, so in any case, it's like that sort of makes sense, right? Because all of these entries, it's like in this series remain square matrices, right, of the right dimension. So you can ask yourself, so as a formal series, it's like this makes sense. So you still have to check that this converges, all right? So as a formal series, this makes sense. As all entries, or all terms, are square matrices, right? Okay, so we still need to check that the series converges. And so to do this, we need to see what happens to the tail of the series. Tail of the sum. Okay, so what I mean is that I'm going to look at the sum from, say, k equals to m to infinity of 1 over k factorial a to the k, and then I want to see that in some appropriate sense, it's like this is going to go to 0. It's like as m goes to infinity. Okay, so let's look at the norm of this. Right, so you can ask, well, what kind of norm should you have? It's like on a matrix, and then the most natural norm, it's like on a matrix, is what's called the induced norm. All right, and so that's what we're going to use here. It's like we're going to look at the induced norm. It's like of some which is induced by some given norm on Cn, right, which is just this vector space which it works on. Okay, so you have this, and this is obviously less than equal to the sum from k k equals to m to infinity 1 over k factorial a, the induced norm of a to the k. And then this is going to be less than equal to the sum from k equals to m to infinity of 1 over k factorial, the induced norm of a to the kth power. Okay. And of course, this last term is nothing more than the tail. It's like associated with the usual exponential function, right? So this is just the tail of the scalar exponential for z is equal to the norm of a. All right, so we know that this, so that goes to 0 as m goes to infinity. Okay. So you need to know that this space of n by n matrices is complete with respect to the given norm. But if you have that completeness result, it's like then what will happen is that this matrix exponential is well defined. Okay. So all right. So let's that's the first part. So let's see what happens now. Okay. So now instead of just a matrix, it's like what I'm going to do is I'm going to multiply it. It's like by some scalar. So if t is a real variable, right? Then we know that t times a is equal to a times t. All right. And what then happens is that e to the at is going to be the sum from k equals 0 to infinity of 1 over k factorial, right? At to the kth power. All right, and what's going to happen is because it's like scalar, so the scalar matrix multiplication, it's like doesn't depend on the ordering, right? You can take the t's out basically. All right. So because of this, right, what happens is that at to the kth power is equal to t to the k, a to the k. All right. So this is going to be the sum from k equals 0 to infinity t to the k over k factorial a to the kth power. Okay. All right. And then if you differentiate with respect to t, right, then this gives you that d dt of e to the at, right, is just a e to the at. Okay, let me sort of maybe work that out in a bit more detail. Okay, so e to the at is the sum from k equals 0 to infinity t to the k, k factorial a to the k. So I guess before I go on, it's like you might think that this sort of fact that it commutes is trivial, but it's sort of less trivial if T was a matrix, right? So in general, obviously, if you have A and B, which are square matrices, B times A is not equal to A times B. And that has important consequences, because what happens then is that at least with scalar exponentials, the exponential of, say, t plus s is equal to the exponential of t times the exponential of s. That is no longer generally true if we're talking about exponentials of matrices. So this is sort of an aside, right? So if A, B are matrices, then in general they don't commute. general A times B is not equal to B times A. And then in that situation, the exponential of AB is not equal to the exponential of A times the exponential of B. Okay, so one has to be careful about this. Okay, I mean, there are sort of ways to figure out it's like what that product is. It's like, but it will involve sort of commutators, so one has to be a little bit careful here. Okay, so that's just something to keep in mind as you go from exponentials of scalar values to exponentials of matrices. So if again, if A and B are matrices which do not commute with each other, right, under sort of matrix products, right, then the exponential of the product is not equal to the product of the exponentials. So that's something which is very important to keep in mind. Okay, so back to this thing about e to the at, right? So I have this. I want to differentiate their respective time. So this is just going to be. So I'm just going to differentiate the sort of things term-wise inside the sum. Right, so t to the k differentiated is k, it's like t to the k minus 1, right? So this is going to be the sum from k equals to 0 to infinity of k t to the k minus 1 over k factorial a to the k. So this is going to be the sum from k equals to 0 to infinity of t to the k minus 1 over k minus 1 factorial a to the k minus 1, right, times a, if you will. Okay, actually, let me write it the other way. A times a to the k minus 1. I'm going to take the a out, right, which I can, okay. So this gives me a, the sum from k equals to 0 to infinity t to the k minus 1. Actually, it's not from k equals to 0 because when k equals to 0, that term, I mean, implicitly going from here to here, I'm dividing by k, right? So, but the very first term corresponding to k equals to 0 vanishes, right? So I can't really divide by k unless k is not equal to 0. So this sum actually is from k equals to 1. And I don't really lose anything by changing the limits of the sum because the k equals to 0 case, this term vanishes. Okay, so that's so I guess there's an intermediate step where for the k equals to 0 case this vanishes, so I can just change the limits of the sum, and then the next step I can divide by k throughout, right, to give me this entry. So anyway, so this gives me all right, so this gives me the sum k minus 1 factorial a to the k minus 1, but I can reindex now to say in L is equal to k minus 1, right? So this gives me a times the sum from L equals to 0 to infinity t to the L over L factorial a to the L, right? And of course, that now is just the exponential of a, so this is just a times e to the, well, exponential of at, right? Okay, so that's basically what happens. So with this calculation, right, you can then state the following theorems. So what we basically showed, right, was that d dt of e to the at is a e to the at. Okay. All right. So let me state the theorem. And the reason, of course, why we are studying matrix exponentials is because you can then express the solution of a system of linear ordinary differential equations in terms of the matrix exponential of this. Okay, so the theorem is that the solution of the initial value problem which is given as follows. Well, actually, x prime is equal to a of x, and x0 is, let's just call that x sub 0, right, is just x of t is equal to e to the at x0. Okay, so the proof is relatively straightforward, right? So if you have x of t is e to the at x0, right, I can just differentiate that. X prime is equal, so there is no time dependence on the x0 term. The only time dependence is coming from this e to the at term. But we showed that d dt of e to the at is a e to the at. So this is a e to the at times x0. But e to the at x0 obviously is x of t. So this is a x of t, right? So the claim then that this thing here, so this thing here satisfies the differential equation, we just need to check that it also satisfies the initial condition. So x at 0 is e to the a times 0, x0, but e to the a times 0 is just the exponential of the 0 matrix, right, which is the identity. So this is the identity times x0, which is just x0. So what we've verified then is that the solution of this form satisfies the differential equation on one hand, and also satisfies the initial condition. So obviously it's a solution of the initial value problem. Okay? So, all right, so that's, again, the motivation for studying matrix exponentials, and that in essence, the problem of solving systems of linear ODEs is equivalent to the problem of computing the matrix exponential. Okay, so what we're going to do next is to talk about how do you actually go about computing this matrix exponential efficiently. So let me just stop here for now.